Hey everyone, welcome back, or if you're just joining us, welcome to KSSP Podcast. I'm Spencer,
I'm Katie.
and in this episode of our series on life cycle of stars, we're going to be talking about white dwarfs, neutron stars, and black holes. So, to start that off, we're just going to be looking at the next chapter in that series of NASA's series, Life and Death of Planetary System. We're going to look at Chapter 7, which is Death and New Life. And their time frame for that is 11 to 13 billion years. So, when the core of the former red giant has exhausted all of its fuel and shed all the gas it can, the remaining dense stellar cinder is called a white dwarf. The white dwarf is considered dead because atoms inside of it no longer fuse to give the star energy, but it still shines because it is so hot. Eventually, it'll cool off and fade from view. Our sun will reach this death about 8 billion years from now. And then we're just going to watch the short little video with that here.
Wow. What was that?
Okay. We'll find out. But that was Chapter 7.
Yeah. That's cool. They said like the death brings new life.
Yeah, and then starts the cycle all over again.
Yeah.
It's kind of interesting how that's like.
I feel like that's just kind of like how the universe is in general.
Cyclical like that.
Yes, exactly. So next we're going to look at white dwarfs. So the first article is white dwarf stars. These are from NASA. So pushing the limits of its powerful vision, NASA's Hubble Space Telescope uncovered the oldest burned out stars in our Milky Way galaxy. These extremely old, dim clockwork stars provide a completely independent reading on the age of the universe. The ancient white dwarf stars, as seen by Hubble, are 12 to 13 billion years old, because earlier Hubble observations show that the first stars formed less than 1 billion years after the universe's birth in the Big Bang. Finding the oldest stars puts astronomers well within arm's reach of calculating the absolute age of the universe. So we've got another article about white dwarf stars. So white dwarf is what stars like the sun become after they've exhausted their nuclear fuel. Near the end of its nuclear burning stage, this type of star expels most of its outer material, creating a planetary nebula. Only the hot core of the star remains. The core becomes a very hot white dwarf with a temperature exceeding 100,000 Kelvin. Unless it is accreting matter from a nearby star, see cataclysmic variables. The white dwarf cools down over the next billion years or so. And because a white dwarf is not able to create internal pressure, gravity compacts the matter inward until even the electrons that compose a white dwarf's atoms are smashed together. So in normal circumstances, identical electrons, or those with the same spin, are not allowed to occupy the same energy level. Since there are only two ways an electron can spin, only two electrons can occupy a single energy level. This is what is known in physics as Pauli exclusion principle. So in a normal gas, this isn't a problem because there aren't enough electrons floating around to fill up the energy levels completely. But in a white dwarf, the density is much higher and all of the electrons are much closer together. This is referred to as a degenerate gas, meaning that all the energy levels in its atoms are filled up with electrons. So for gravity to compress the white dwarf further, it must force electrons where they cannot go. Once a star is degenerate, gravity cannot compress it anymore because quantum mechanics dictates that there is no more available space to be taken up. So our white dwarf survives not by internal fusion but by quantum mechanical principles that prevent its complete collapse. And then degenerate matter has other unusual properties, like the more massive a white dwarf is, the smaller it is. And this is because the more mass a white dwarf has, the more its electrons must squeeze together to maintain enough outward pressure to support the extra mass. However, there is a limit on the amount of mass a white dwarf can have. I'm not going to try to pronounce this name, but Chandrasekhar discovered this limit to be 1.4 times the mass of the Sun. This is appropriately known as the Chandrasekhar limit. The heavier atoms in its atmosphere sink and the lighter ones remain at the surface. Some white dwarfs have almost pure hydrogen or helium atmospheres, the lightest of elements. Also, gravity pulls the atmosphere close around it into a very thin layer. So next, we have Hubble discovers hydrogen burning white dwarfs enjoying slow aging. So now an international group of astronomers has discovered the first evidence that white dwarfs can slow down their rate of aging by burning hydrogen on their surfaces. We found that the first observable evidence that white dwarfs can still undergo stable thermonuclear activity, explained Jianqing Chen of the alma mater Studiorum Università di Bologna and the Italian National Institute for Astrophysics, who led this research. This was quite a surprise, as it is at odds with what is commonly believed. So, this discovery could have consequences for how astronomers measure the age of stars in the Milky Way galaxy. The evolution of white dwarfs has previously been modeled as a predictable cooling process. This relatively straightforward relationship between age and temperature has led astronomers to use white dwarf cooling rate as a natural clock to determine the age of star clusters, particularly global and open star clusters. However, white dwarfs burning hydrogen could cause these age estimates to be inaccurate by as much as 1 billion years. And then lastly, there was a citizen scientist who found an ancient white dwarf star encircled by puzzling rings. And this white dwarf is so old that whatever process is feeding material into its rings must operate on billion-year timescales, said John Deebs, an astronomer at the Space Telescope Science Institute in Baltimore. Most of the models scientists have created to explain rings around white dwarfs only work well up to around 100 million years, so this star is really challenging our assumptions on how planetary systems evolve. Previously, disks and rings had only been observed surrounding white dwarfs around 1/3 of this star's age. Yet some white dwarfs, between 1 and 4%, show infrared emissions indicating that they're surrounded by dusty disks or rings. Scientists think the dust may arise from distant asteroids and comets kicked closer to the star by gravitational interactions with displaced planets. As these small bodies approach the white dwarf, the star's strong gravity tears them apart in a process called tidal disruption. The debris forms a ring of dust that will slowly spiral down onto the surface of the star.
Okay. And then next we're gonna just move on to neutron stars. So my first article I have here again is from NASA, just about neutron stars. So when the core of a massive star undergoes gravitational collapse at the end of its life, protons and electrons are literally scrunched together, leaving behind one of nature's most wondrous creations, a neutron star. Neutron stars cram roughly 1.3 to 2.5 solar masses into a city-sized sphere, perhaps 20 kilometers or 12 miles across. Matter is packed so tightly that a sugar cube size amount of material would weigh more than 1 billion tons, about the same as Mount Everest. So most known neutron stars belong to a subclass known as pulsars. These relatively young objects rotate extremely rapidly, with some spinning faster than a kitchen blender. They beam radio waves in narrow cones, which periodically sweep across Earth like lighthouse beacons. And astronomers have found less than 2,000 pulsars, yet there should be about a billion neutron stars in our Milky Way galaxy. There are two reasons they have for this shortfall. One is age. Most neutron stars are billions of years old, which means they have plenty of time to cool and spin down. Without much available energy to power emissions at various wavelengths, they have faded to near invisibility. But even many young pulsars are invisible to us with radio telescopes because of their narrow lighthouse beams. Because pulsar beams are much broader and gamma rays, GLAST will allow us to detect some of the youngest, most energetic pulsars in our galaxy, says GLAST interdisciplinary scientist Stephen Thorsett of the University of California, Santa Cruz. Getting a much more complete sample of the Milky Way's population of neutron stars is one of the most important ways that GLAST will advance their understanding of the life cycle of stars. And GLAST is... I thought it said somewhere, but I'm guessing it's one of like their telescope monitoring.
Yeah, I would think.
Something like that, yeah. So then the next article I have here is again from NASA. And it's NASA's retired Compton mission reveals super heavy neutron stars. So, astronomers studying archival observations of powerful explosions, called short gamma ray bursts, or GRBs, have detected light patterns indicating the brief existence of a super heavy neutron star shortly before it collapsed into a black hole. This fleeting massive object likely formed from the collision of two neutron stars. And they looked for these signals in 700 short GRBs detected with NASA's Neil Gell Swift Observatory, Fermi Gamma Ray Space Telescope, and the Compton Gamma Ray Observatory, explained Cecilia Sciurenti, a researcher at the University of Maryland College Park and NASA's Goddard Space Flight Center in Greenbelt, Maryland, who presented the findings at the 241st meeting of the American Astronomical Society in Seattle. They found these gamma ray patterns in two bursts observed by Compton in early 1990s. So, with this article, we have a video, and the video is a simulation that tracks the gravitational wave and density changes as two orbiting neutron stars crash together. Dark purple colors represent the lowest densities. White, yellow, white shows the highest. An audible tone and a visual frequency track the steady rise in the frequency of gravitational waves as the neutron stars close. When the objects merge at 42 seconds, the gravitational waves suddenly jump to frequencies of thousands of hertz and bounce between two primary tones. The presence of these signals in such simulations led to the search and discovery of similar phenomena in the light emitted by short gamma ray bursts. So we'll watch that short video here.
Oh.
Okay. Oops. Okay. Interesting.
Yeah.
And then we'll move on to the next article, again from NASA. So, this is NASA's NICER probes the squeezability of neutron stars. So, matter in the hearts of neutron stars, dense remnants of exploded massive stars, takes the most extreme form we can measure. Now, thanks to data from NASA's Neutron Star Interior Composition Explorer, or NICER, an X-ray telescope on the International Space Station, scientists have discovered that this mysterious matter is less squeezable than some physicists predicted. This finding is based on NICER's observation of PSR J0740 plus 6620, J0740 for short, the most massive known neutron star, which lies over 3,600 light years away in the northern constellation Camelopardalis. So J0740 is in a binary star system with a white dwarf, the cooling remnant of a sun-like star, and rotates 346 times per second. Previous observations place the neutron star's mass at about 2.1 times the sun. So with that, we have another video here, and it's going to watch how NASA's neutron star, NICER, is helping physicists peer into the hearts of neutron stars, the remains of massive stars that exploded in supernovae. Scientists want to explore the nature of matter inside these objects, where it exists on the verge of collapsing into black holes. To do so, scientists need precise measurements of neutron stars' masses and sizes, which NICER and other efforts are now making possible. So, NASA's NICER tests matters limits by NASA Goddard.
Matter at the heart of a neutron star, the crushed remnant of a massive sun, is on the brink of becoming a black hole. For decades, scientists have wondered about the properties of that matter, the densest in the universe we can measure, and what form it takes. Now they have new insights thanks to NASA's NICER X-ray telescope on the International Space Station. A neutron star forms when a massive star's core runs out of fuel. With nothing left to fight gravity, the star collapses. Here, protons and electrons crush together to form neutrons, as well as lightweight particles called neutrinos that escape the star. The core continues to collapse until the matter at its center has twice the density of an atom's nucleus, but on a city-sized scale. When the core can't compress further, it rebounds. The expanding core crashes into the star's collapsing inner layers, creating a shockwave that rips outward through the star. The result is a powerful supernova explosion with a newborn neutron star at its center. Scientists have many questions about neutron star physics, including how squeezable is the matter in their cores? In more squeezable models, the internal pressure and density break neutrons in the center into a sea of even tinier particles, or combinations of those particles, resulting in a squishy core and a smaller star for a given mass. In some less squeezable models, the neutrons hold up against those forces, resulting in a larger star. Scientists used NICER's precise mass and size measurements of two pulsars, a kind of rapidly rotating neutron star, to narrow down how compressible these objects are. A pulsar is so dense that its strong gravity warps nearby space-time, allowing us to see light emitted from its far side. This distortion makes it look bigger than it actually is. The more massive the pulsar, the greater the warping and the larger it appears. Scientists measure this distortion by tracking the brightness of X-ray emitting hotspots on the pulsar's surface as it spins. They can then precisely determine the pulsar's mass and radius and obtain important clues about conditions in the core. NICER used this method to analyze J0740, the heaviest known pulsar with about 2.1 times the sun's mass. Two research groups using different approaches both estimate it's about 16 miles across. NICER's measurements of J0740 and pulsar J0030 disfavor squeezable models, where cores contain only quarks or other exotic matter. And J0740's size and mass together challenge less squeezable theories, where cores contain only neutrons. Physicists will have to develop new models, perhaps containing both neutrons and quarks, to explain NICER's observations. The cores of neutron stars represent matter's final, stable form, short of becoming a black hole. Scientists can't recreate those conditions in Earth laboratories, so NICER will continue to measure pulsars, to probe deeper and deeper into the hearts of these mysterious objects.
Okay. Oh,
Just
interesting. I always like how they can always end up finding new things, unexpected things, like how
yeah.
this doesn't match either of their models, so now they kind of have to come up with a new model theory. I
Yeah.
always find that I love science like that, where we never sometimes we don't know, and we think we know, and
Sometimes,
then
yeah.
we find out what our theories weren't exactly right, so then we have to adjust them a little bit, and that's always interesting.
Right. And then we find that through a lot of, testing and math and
Yes.
all that fun stuff.
And then I have a couple more articles here from NASA. This one is Powerful Neutron Stars Behavior Surprise IXPE Researchers. So in February of 2022, NASA's Imaging X-ray Polarimetry Explorer (IXPE) observed its first accreting neutron star, Hercules X1, more than 21,000 light-years from Earth. Now, a new study based on those observations has upended traditional assumptions about neutron stars and their interior processes that drive these ultra-powerful objects. So, Hercules X1 isn't alone in space. It has companions, star in close proximity, and because of its powerful gravity, strips that neighbor of its outer layer of gas. That feature makes it an accreting neutron star, meaning it pulls streams of hijacked energy and particulate matter from the so-called donor star. It's dragged along the neutron star's own intense magnetic field lines and forms an accretion disk around Hercules X1. So Hercules X1 is also a pulsar. Pulsars are neutron stars which rotate faster and faster as their cores collapse, emitting powerful beams of electromagnetic radiation. These energetic strobes register as pulses detectable across distances of thousands of light years by IXPE and other telescopes. So scientists know a lot about the strength of a neutron star's magnetic field, Hurt noted, but have yet to fully grasp the physical structure of that field, how and why it fluctuates over time, and the relationship between a accreting neutron star and its donor star. And that is where IXPE really shines, said Brian Ramsey, IXPE principal investigator at Marshall. The effects we infer from polarization are impossible to see directly, operating on scales we could never hope to capture using conventional means. IXPE is helping us document the behavior of the invisible world. So, such a large discrepancy implies that our ideas about how X-rays are generated in Hercules X1 and possibly other pulsars will need to be substantially revised, said Juri Potinen of the University of Turku, Finland, who leads IXPE research into accreting neutron stars. The system has previously showed regular variations in brightness with a period of 35 days. Despite two stars orbiting each other every 1.7 days, such fluctuation could indicate what is known in astrophysics as precession, an ongoing process of slow changes to a celestial body's orbital or rotational parameters. In other words, the accretion disk could be warped or wobbling as it spins. So, yeah, just kind of some new stuff they're learning about neutron stars. And then the last little article here from NASA again is astronomers spot a distant and lonely neutron star. So they have discovered, and astronomers have discovered a special kind of neutron star for the first time outside the Milky Way galaxy. Neutron stars are the ultra-dense cores of massive stars that collapse. This newly identified neutron star is a rare variety that has both a low magnetic field and no stellar companion. It's located within the remains of a supernova in the small Magellanic Cloud located 200,000 light years from Earth. Oxygen-rich supernova remnants are important for understanding how massive stars fuse lighter elements into heavier ones before they explode. Seen up to a few thousand years after the original explosion, oxygen-rich remnants contain the debris ejected from the dead star's interior. This debris is observed today hurtling through space after being expelled at millions of light years per hour. The lack of evidence for extended radio emissions or pulsed X-ray radiation, typically associated with rapidly rotating, highly magnetized neutron stars, indicates that astronomers have detected the X radiation from the hot surface of an isolated neutron star with low magnetic fields. About 10 such objects have been detected in the Milky Way galaxy, but this is the first one detected outside our galaxy. But how did this neutron star end up in its current position? Seemingly offset from the center of the circular shell of X-ray emission produced by the blast wave of the supernova. One possibility is that the supernova explosion did occur near the middle of the remnant, but the neutron star was kicked away from the site in an asymmetric explosion at a high speed of about 2 million miles per hour. However, in this scenario, it is difficult to explain why the neutron star today is so neatly encircled by the recently discovered ring of gas seen at optical wavelengths. Another possible explanation is that the neutron star is moving slowly and its current position is roughly where the supernova explosion happened. In this case, the material in the optical ring may have been ejected either during the supernova explosion or by the doomed progenitor star up to a few thousand years before. So, yeah, just a lonely neutron star, and they're wondering why. Trying to figure out why. But yeah, so that's some articles that we had on neutron stars.
Right. And now we can move on to black holes. So, what is a black hole? A black hole is an astronomical object with gravitational pull so strong that nothing, not even light, can escape it. A black hole's surface is called its event horizon, and it defines the boundary where velocity needed to escape exceeds the speed of light, which is the speed limit of the cosmos. Matter and radiation fall in, but they can't get out. So two main classes of black holes have been extensively observed. Stellar mass black holes with 3 to dozens of times the sun's mass are spread throughout the Milky Way galaxy, while supermassive monsters weighing 100,000 to billions of solar masses are found in the centers of most big galaxies, including ours. So a stellar mass black hole forms when a star with more than 20 solar masses exhausts the nuclear fuel in its core and collapses under its own weight. The collapse triggers a supernova explosion that blows off the star's outer layers, but if the crust core contains more than about 3 times the sun's mass, no known force can stop its collapse to a black hole. The origin of supermassive black holes is poorly understood, but we know they exist from the very earliest days of a galaxy's lifetime. Once born, black holes can grow by accreting matter that falls into them, including gas stripped from neighboring stars and even other black holes. Although light can't escape a black hole's event horizon, the enormous tidal forces in its vicinity cause nearby matter to heat up to millions of degrees and emit radio waves and X-rays. Some of the material orbiting even closer to the event horizon may be hurled out, forming jets of particles moving near the speed of light that emit radio, X-rays, and gamma rays. Jets from supermassive black holes can extend hundreds of thousands of light years into space. Interesting. So the next article, the Hubble finds hungry black hole twisting captured star to donut shape. I believe we have a video for that.
Yes, so this video is Hubble finds hungry black hole twisting captured star into donut by NASA Goddard. And we'll watch that here.
Using NASA's Hubble Space Telescope, have recorded a star's final moments in detail as it was ripped apart and eaten up by a black hole in a tidal disruption event. The shredded star is nearly 300 million light years away, but astronomers used Hubble's powerful ultraviolet sensitivity to analyze its light to gather forensic clues of the violent event. Hubble data found a very bright, hot, donut-shaped area of gas the size of the solar system swirling around a black hole. The swirling gas was once a star.
Can you pause?
Usually, astronomers get just a few...
Yes.
Something I just realized to help remember. So there's infrared and ultraviolet. Like, I'm just now realizing that it's infrared and ultraviolet because they're on the ends of the color spectrum. So like red is on one end of the color spectrum and violet is on the other end. So there's infrared and ultraviolet. You know, that's why it's those two.
Oh, I never knew that either.
I just realized it now, so I was just looking at this color scale or whatever. And yeah.
I didn't even notice that either, but yeah, no, I didn't know that, so now we all learned, or maybe not some, but we learned something new, so.
Yeah, we learned this together.
Few observations at the beginning of a disruption event when it's very bright, but this energetic collision's proximity and brightness allowed Hubble to gather ultraviolet data over a longer than normal time period. This is a rare opportunity for scientists to create models of what they think is going on and then compare those models with what Hubble sees. It is an exciting place for scientists to be, right at the intersection of the known and the unknown.
Okay.
Cool. All right, so black holes are gatherers and not hunters. They're gonna lie in wait until a helpless star wanders by. When the star gets close enough, the black hole's gravitational grasp violently rips it apart and sloppily devours its gases while belching out intense radiation. These are termed tidal disruption events, but the wording belies the complex raw violence of a black hole encounter. There's a balance between the black hole's gravity pulling in star stuff and radiation blowing material out. So, in other words, black holes are messy eaters. Astronomers are using Hubble to find out the details of what happens when a wayward star plunges into the gravitational abyss. And then we've got new NASA black hole sonifications with the remix. We've got 2 videos for that.
So the first one is data sonification, black hole at the center of the Perseus galaxy.
Creepy.
Right?
So cool.
And then the second one we have is data sonification, black hole at the center of galaxy M87. That one was so much more calming.
Yeah, that's so weird.
Yeah, it's
They all sound
interesting.
so different.
Yeah, that's very interesting.
Yes. So, okay, there's a popular misconception that there is no sound in space, and it originates with the fact that most of space is essentially a vacuum, and that provides no medium for sound waves to propagate through. But a galaxy cluster, on the other hand, has copious amounts of gas that envelop the hundreds or even thousands of galaxies within it, and that provides a medium for the sound waves to travel. In this new sonification of Perseus, the sound waves astronomers previously identified were extracted and made audible for the first time. So the sound waves were extracted in radial directions, that is, outwards from the center. The signals were then resynthesized into the range of human hearing by scaling them upwards by 57 of 58 octaves above their true pitch. So another way to put this is that they're being heard 144 quadrillion and 288 quadrillion times higher than their original frequency. The radar-like scan around the image allows you to hear waves emitted in different directions. So then we have one more article here, and that is the Hubble determines mass of isolated black hole roaming our Milky Way galaxy. There's a video with this one as well.
And that is Hubble measures potential isolated black hole roaming galaxy by NASA. Go ahead.
Black holes roam our Milky Way galaxy. These objects are invisible and so very difficult to detect. Astronomers now believe they may have precisely measured the mass of an isolated black hole for the first time. After 6 years of observations, NASA's Hubble Space Telescope found evidence for a lone black hole about 5,000 light years away, wandering through interstellar space. Black holes roaming our galaxy are born from rare monstrous stars, less than 1,000th of the galaxy's stellar population, that are many times more massive than our Sun. These stars die in supernova explosions, their cores crushed by the star's own gravity into a black hole. Because the detonation is asymmetrical, the black hole may get a kick, sending it careening through our galaxy. Hubble detected the magnified and deflected light from a star lined up exactly behind the potential black hole, as its intense gravity warps space itself. The measurements indicate the black hole weighs 7 solar masses and is traveling through space at 100,000 miles per hour. But don't worry, there's a lot of space between Earth and this roaming black hole.
Okay.
All right. So yeah, astronomers estimate that 100 million black holes roam among the stars in our Milky Way galaxy, but they never have conclusively identified an isolated black hole before. Following 6 years of meticulous observations, the Hubble Space Telescope has, for the first time ever, provided direct evidence for a lone black hole drifting through interstellar space by a precise mass measurement of the phantom object. Until now, all black hole masses have been infrared statistically, or through interactions in a binary system or in the cores of galaxies. Stellar mass black holes are usually found with companion stars, making this one unusual. The signature of a foreground black hole stands out as unique among other microlensing events. The very intense gravity of the black hole will stretch out the duration of the lensing event for over 200 days. Also, if the intervening object was instead a foreground star, it would cause a transient color change in the starlight as measured because the light from the foreground and background stars would momentarily be blended together. But no color change was seen in the black hole event. And the existence of stellar mass black holes had been known since the early 70s, but all their mass measurements until now have been in binary star systems. Gas from the companion stars falls into the black hole and is heated to such high temperatures that it emits X-rays. About 24 black holes have had their masses measured in X-ray binaries through their gravitational effect on their companions. Mass estimates range from 5 to 20 solar masses. Black holes detected in other galaxies by gravitational waves from mergers between black holes and companion objects have been as high as 90 solar masses.
And now that we've gone over the different stages in a star's life cycle, make sure to join us in our next video where we kind of just provide a brief summary of what we've gone over and share our thoughts. And don't forget, you can always leave a comment below letting us know if you have any ideas for future topics you'd like us to go over.
You can also reach out to us on Facebook, YouTube, Instagram, Twitter, and TikTok, and we also occasionally do Twitch live streams.
So don't forget to like, follow, or subscribe, and turn on notifications so that you know when we do. Otherwise, we will see everyone in the next video.